This is the Amp Hour Podcast. Released May 30th, 2023. Episode 634. The CAN Bus Can with Dr. Ken Tindell. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
And I'm Dr. Ken Tindell, CTO of Canis Automotive Labs.
Hi, Ken. How you doing?
I'm doing great.
You and I met the way that I have met many other people before, which is on Twitter or equivalent, now Mastodon. Someone said, Chris, you're very wrong. And I said, yes, I get to learn new things from Dr. Ken. So thank you for doing that. And thanks for reaching out.
Yeah, you're welcome.
Ken basically said, he heard our last one about the noisy CAN bus or a couple episodes ago. And he said, well, you were wrong. And here's some of the stuff why. And then I was like, who is this person? And then I realized that he had just posted this link that I was about to talk about the next show, which was like the most awesome link, which we're going to talk about today. But it was about the CAN bus and people breaking in through people's headlights into cars and then doing CAN injection, all this crazy stuff. So really excited to hear about that stuff.
Excellent. Yes, that's good fun.
So tell us about your company. Canis Labs is your company. You've been in the space for a long time. What drew you to it in the first place?
So I've been in automotive since 1995, very long time. And in fact, the first company I founded is now part of Bosch, doing real-time operating systems inside cars. But Canis Labs is focused on car security, because that's a big topic. And we're focused on securing the CAN bus, which is also a big topic.
Yeah, right.
So that's where this CAN injection stuff came from. Is a friend of mine, Ian Tabor, is a cybersecurity researcher for automotive, and he had his Toyota RAV4 stolen, and so he started a lot of sleuthing about exactly how they stole his car, because it shouldn't have been possible. And then he found out it was somebody had tapped into the CAN bus, and he went and bought the theft device they used and called me in as a CAN bus guru, and we together reverse engineered exactly how that theft device worked, and then we wrote it up.
Yeah, I was surprised at the form factor of this theft device as well. Can you explain that?
Yeah, so it's quite fair. People have misunderstood it. In fact, exactly as it was intended. So this is sold and marketed as a emergency override, as if it's kind of somehow legitimate.
Right. My lockpick system, sir, is not for breaking into cars. It's for when I get locked out of my home, sir.
Yeah, exactly. and that's why they have a JBL Bluetooth speaker, and they have added a little bit of electronics inside. And so what appears to be the USB cable is actually a twisted pair CAN bus. So if you are stopped by the police, you're not going equipped. You've just got a little Bluetooth battery-powered speaker on you, and therefore you're not a criminal. But that's why it's disguised like this, because of course that's how an owner would want their emergency override thing disguised, wouldn't they?
Of course, yeah. Just so that you can. It doesn't even double. Does it still operate as a Bluetooth speaker or no?
I think it might even. Oh no! Sorry, they've ripped one of the connectors off internally, so it probably doesn't work.
Yeah,
but it uses the battery to power the device.
Right. It's like the working can of shaving cream when you're stealing all the embryos at Jurassic Park. That's the important thing, right? You got to have the plausible deniability.
That's a perfect analogy.
Yeah, that's great. I mean, and as you said in the post too, it's eye-watering how much it costs. I mean, how much does one of these things cost if you buy it on the great?
It depends on the model of car it's the firmware's tailored for.
Oh, yeah.
I think they're selling it for €15,000 if you want to use it to steal really high-end Jaguars.
Huh.
Yeah, this one's $2,500, I think, for RAV4s.
Mm-hmm. That's nuts. Yeah, I guess maybe you get more volume, but you have to make it up in volume. You don't get the high end cost per vehicle. But Okay, so then your friend had this car stolen. How did they actually steal the car?
Okay, so it was actually interesting, because this was on Twitter back when I was on the bird site, as they call it now, on Mastodon.
Mm-hmm.
And I saw a tweet go by, really angry about how they'd vandalized his car and come along and pulled some of the trim off on the front of his car, and he thought it was vandalism. Turns out in retrospect it wasn't. It was just incompetent thieves. And then they came back again and loosened it up, and he thought again they've tried to vandalize it again, but either it was the same gang practicing or a different gang. So he got really, really angry, and that was the second tweet I saw. And then the third tweet was the next day, I think, saying, "I know what they were doing. They were stealing my car." And that's where he started investigating why the hell you would pull off the connector on the headlamps to steal a car. And of course, he's got links into police forensics and stuff, and was pointed at this JBL Bluetooth disguised theft device. So he went and bought one with his own money, and that's when we started to rip it apart. So the electronics inside the theft electronics is covered in a big blob of resin to try and deter thieves from thieving from the thief.
No honor amongst them, apparently.
Yeah, exactly. So So Ian did most of the heavy lifting on pulling electronics apart and pulling schematics together and stuff. And it's basically about $10 worth of electronics inside. So that's quite a markup.
Wow.
From selling that. So it's a PIC 18F with an on-chip CAN controller and a CAN transceiver and their own little magic CAN transceiver add-on circuit, which I won't describe just because I don't want to make it easy for someone to replicate all of this.
Right. Yeah, I mean, it is amazing that this is. I mean, it does feel kind of like a blunt device in a certain way, but also like it's how you program the blunt device that ultimately does this sort of thing.
Yes.
Maybe we could step back a little bit. So you know, we were talking about CAN bus. I had described it as a noisy, rude bus, and that was not pleasing to your ears. Can you just explain what CAN bus is?
Yeah, so CAN bus, that dates back to the mid-80s. So it's designed by a protocol designed by Bosch. And it's designed what they called multiplex. So at that point in time, anytime you wanted sensor information from somewhere to somewhere else, like a speed signal or something, you ran a little copper wire. So it would have a PWM encoded speed signal or an analog encoded battery voltage or something like that. And they'd just be running bundles and bundles and bundles of wires around. And pretty soon, the car becomes less made of steel and more made of copper, and it was just running out of control. So what CAN is designed for is to replace lots and lots and lots and lots of little individual signal wires with one twisted pair multi-drop bus, so that you broadcast your signal values, and every other node on the bus gets to see those signals, and if it's needs them, react accordingly. So CAN is what they call a publish-subscribe model. So you publish all your sensor values, and then subscribers pick up them if they want them, and do something with them if they want to. So it's a pretty simple system.
And we have talked about car harnesses before, and I think what you were getting at there as well is that like the number of wires really explodes if you don't have some bus system, because now you have point to point and it becomes this insane thing. And some of them are going front of car to back of car. And if you had like even just the the tail lamps, I'm sure on most cars would start to become over the top, you know, like just to be able to control those things.
Yeah. So the first car company I ever worked with was Volvo. And they showed me a presentation where they plotted a graph of all of the functions in the car over time, looking at all the signals and all the increased functionality they expected in new models and so on. And they drew that curve, an exponentially increasing curve. And at some point, the wires would weigh more than the car. And that's kind of, it obviously can't get to that. It's just broken. Right. So that's why everyone moved to this multiplex solution. And that's what CAN was for.
Okay. Can you also, I've heard of LIN bus as well. Can you disambiguate CAN bus from LIN bus?
Yes, I can, because I was there at the very start of LIN bus. So my co-founder, Antal Reinek of Canis Labs, he was working with Volvo on the same P2X car platform, and they were looking for something that was cheaper than CAN even, because back then CAN wasn't as cheap as it could be. And there were a lot of systems where you had little packs of buttons and so on. Very, very slow. You just need a button on, button off, maybe a little LED to say the button is on, and so on. And they wanted something that was like CAN, but very, 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 very cheap. So LIN is designed to be like the little brother of CAN that runs very, very slow on a single wire, because that's the cheapest. One wire is cheaper than two. And it uses, basically you bit bang the entire protocol in software in a microcontroller that is so cheap and small, everything's been stripped out, even the UART. That's the original concept.
Oh, wow.
Yeah. And then it's a kind of a master-slave protocol. So the transmitter sends out a header for the frame it's looking for. It knows about the schedule on the bus, and it just says, I want this one, now I want this one, now I want this one. And then all the little devices respond with the corresponding frame.
And then would the master have a CAN bus out the back in order to like bridge the two?
Yes, exactly. So normally you'd have a full fat ECU with a metal box and a CAN bus connector on it, and then it would run out a few little local wires, and then strung off of each of those would be your switch packs and so on. So the steering wheel is a good example. So that there is a steering wheel ECU, but instead of running 25, 30 wires into that ECU, you run a LIN bus around the steering wheel, and it's directly connected up to the button packs that are then molded into the steering wheel.
Huh.
And then, yes, the ECU then gateways the information onto CAN bus and publishes it.
Huh. Okay. I mean, it does seem as well, like, I mean, looking at cars, and it does seem like they're increasingly, even though they've had electronics for a long time, I'm a long time car talk listener, they, like Tom and Ray would talk about relays and all that stuff, and not just about the starter, but even the lights and the blinkers and whatever, it's all that stuff is in really old cars too. But increasingly, like, just there's so I remember seeing an estimate of like 200 some micros per car, or maybe even higher now. I like what is an approximation of a modern car, like the amount of electronics in it?
God, I mean, it'll vary a little bit depending on high end and low end cars, but 50 ECUs is probably now around average. So a low end car might have 20, and a reasonable average car might have 50 ECUs, and then the high end cars up to 100. And then, so each ECU's got a microcontroller in it.
Mm-hmm.
And then all the LIN buses, they've all got microcontrollers. So you're probably looking at 5 or 10 microcontrollers on each LIN bus, and there might be several dozen even LIN buses in a car. So I think if you added up the number of microcontrollers, you could be looking at 700 per car, 500, something like that as an average.
Yeah, right. And during the chip shortage, you don't get a single one, you can't ship the car. Well, or you start without functionality.
Yeah. So I saw presentations from people saying we need rapid portability of software to whatever's available from the vendor.
Right.
Yeah, really, it was really tough, and you had to play. It was a horrible game of like, well, can we just live without this ECU then? And so you start to see cars with options just missing.
Huh.
Yeah, it was really bad.
Yeah, it'll be an interesting, like the Kelly Blue Book, or whatever the equivalent is worldwide. It will have a tough time valuing cars. Like, which options did you have enabled? You bought this car in 2021. Okay.
Yeah, that was just really bad. Oh,
yeah. I remember my first experience with CAN bus was not actually using it. It was just, I remember sitting in a presentation with Freescale, and the sales guy, he's like, "So do you need CAN in your in your micro?" And I'm like looking at him like a soda can. I didn't know what it was at the time, and it was obviously Freescale was big into that space, and they wanted to sell more things with CAN bus because you could charge more for it. But yeah, I mean, it's certain chip vendors that really kind of play in the space too.
Yeah, so in fact, I started working with them in this Volvo project back when they were called Motorola still, and before they spun out to Freescale.
Yep. Now in XP as well, of course.
Now in XP, yeah. So
rest in
Philips
peace. Right.
merged up, yeah. Although Philips are an early CAN provider as well.
Oh, sure.
Yeah. So we worked with them on designing the MS CAN controller, which was designed to be very, very, very low cost on chip CAN controller. So it had a very, very small amount of buffers. There's a clever thing you need to do with CAN, which is to make sure that when you are queuing multiple CAN frames, that you send the highest priority one first out of your CAN controller. It sounds obvious, but it's actually quite hard to do that, right? So the MS CAN was designed to automatically work out which is the highest priority CAN frame in its little tiny buffers, and then send that one first. And that's what we worked with Freescale on designing that. And then everyone ever since for these little low end CAN controllers has copied that model. Which is nice to see.
Let's take the perspective of a microcontroller now. So I'm a little ECU microcontroller, and I have a sensor reading I want to publish onto the bus. What am I seeing whiz by, and what else is happening? How do I actually get me as the tiny little microcontroller? How do I get my piece of data onto the bus? So, like, from that perspective.
Yeah, it's that's one of the things that CAN's so good at. Is it's a prioritized bus. So rather than being rude and noisy, it's the most polite bus there is, because the most urgent traffic gets the highest priority, and then the protocol basically says who's really important, got something really important. Oh, and then you go first, and we'll come later. And then now you're the most important, and you go first.
The highest priority is the lowest address. Is that how do we define priority as well?
Yeah. This is one of the most confusing things about CAN, because it's got what's called an identifier field that goes first, and the identifier is used both to identify the contents of the frame, obviously, but also the priority. So it's got two features for one field, and this always causes confusion, of course. When, in fact, generally speaking, when you have one thing used for two purposes, everyone gets confused. So the primary purpose in the protocol is to make sure that the lowest number goes first. And the way it does that is everything jumps in at start of frame, and then you transmit onto the bus. And the bus works like a giant AND gate. The way the transceivers work is everything floats to level 1, and then if you assert a 0, you pull the voltages together. So everything floats to 2.5 and minus 2.5, and that's encoded as a 1. And then if you've got a 0 to send, you pull the bus you pull those two lines together, and that's your 0 point. And then what happens is the protocol runs a little state machine. So everyone sends their first bit, and you read it back. And if you read back something different to what you sent, you can't be the highest priority, because the 0, the first person with the 0 in the current bit must be the higher than you. So you back off and wait until the next CAN frame starts, and that just goes down the field bit by bit. And when you get to the end of those, with CAN, it's by default 11 bits, but it can be longer. Then you must be the highest priority frame on the bus, and then you get to carry on sending the rest of your frame, and everyone else switches over to listening to it to receive it.
My second experience with CAN was at ABB. We were using RS-485, and we basically did lowest address wins, and we were telling some vendor about it, and they go, "Oh, you guys remade CAN bus," and I was like, "Oh, okay."
Yeah. Well, I had the privilege of speaking to one of the guys at the Bosch team that developed CAN, Professor Kinker, and he said that's how they started. They were looking to do 485 multi-drop and an addressing scheme, and then that's what they succeeded in doing. But it turned out to be too much CPU load, so they put it into hardware, and that became CAN.
Right. And when you're Bosch, you get to just make new standards.
Yeah, exactly. So it's like, well, we're
Chris
going to put
Gamble doesn't get to make new standards, nor does even an ABB team. But Bosch, you get to do whatever you want, basically.
Yeah. There's probably billions of CAN controllers.
It's good to be king. It's good. Yeah. Okay, that's cool. All right. So that is how it is not a noisy, rude bus, but in fact a very polite bus. That was the point of one of many points of contention. Okay, I get that. I'd like to defend myself a little bit, only in that what happens when I, as an outsider, as a CAN dummy dum dum, let's say, when I start looking at CAN traffic, it looks like insanity.
Yeah.
And how does one start to unwind that as an outsider?
Right. So the normal model is that, originally it was conceived that your identifier said, I am a temperature sensor, and the next identifier said, I am the front left wheel speed, and so on. But very quickly, you realize that the CAN protocol has a lot of overhead to carry a very small amount of data. So people started to pack many signals into one CAN frame. So that's 60 up to 64 bits, 8 bytes. So they would pack lots and lots of stuff in. So most CAN buses today will have like 12, 15, 20 signals, so they call them, packed into that field. And they're at particular bit patterns. And then you transmit the CAN frame with those values in 10 millisecond period, 100 millisecond, 50 milliseconds, depending on what you know the receiver needs of how stale the data can be and still be useful.
Okay.
So when you connect up to CAN bus, there is a blizzard of 10 millisecond frames and 20 millisecond frames and 50 millisecond frames, and they all go by, and there's this vast list of frames bumbling along. And if you want to know what goes on, you've got to kind of like focus on a particular ID, and then you've got to focus on a bit position within the payload to pull that out. And if you want to try and reverse engineer it, that can be really quite difficult. There are some tools to help you reverse engineer it from scratch that look at the rate at which bits change. So you would expect the least significant bits to change fastest on a signal that was moving a little bit. And that tells you where the least significant bit probably is in the bit pattern. And then you kind of reverse your way forward. I've just updated a protocol decoder for a logic analyzer. This is the SIGROC protocols.
Oh, cool.
And that, if your logic analyzer is up to it, what that will do is look at very, very, very fine changes in the way in the duration of the bit, because depending on where you are on the CAN bus, you get little reflections up and down that are down to impedance mismatches, and that affects the rise and fall time depending on when those reflections come in, and it's deterministic based on where you are in the bus. And if you can measure accurately those times, you can then start saying which physical device the CAN frame came from. So you can start to put together a pattern of this ECU is transmitting, and this one is transmitting from here, and these 7 frames come from this ECU, and so on. And then with that signaling pattern, based on rates of bit changes, you can probably start to guess. And then you have to play a game of, well, when I turn on the lights, this one seems to change, and so on.
I see. Yep.
The car makers, of course, know all of this. So
The logic analyzer thing is almost kind of sounds like almost like a time domain reflectometry, but like mapped CAN. Is that a fair comparison?
yes. So, but what it does is actually it only does the digital side from the transceivers. So you don't get to see any voltage changes, but the effect. So basically, if the patterns will reflect up just the right way, then they will hasten the transition from one state to the other. And if they are in different timings, then they arrive when the state's already changed, because of hysteresis and stuff in the transceiver. They're kind of ignored. And the way those reflections rattle up and down the bus, bouncing off the ends back and forth.
Yeah.
It just turns out that you can use these very small changes to correlate frames from the same source.
Got it. That sounds like some very advanced stuff. Like most,
it's actually quite
sounds
easy.
like that's what a researcher would do versus like a generic user. Is that fair or no?
Oh yeah. No, this is advanced stuff. The reason I know about this is because I've been working on the CAN HG protocol, which augments CAN to give it a lot more bandwidth, and then to put some security headers and things.
Got it.
Basically, it puts out of band data in the gaps inside slow CAN bits. So if you run your CAN bus at, say, 250 kilobits, which is kind of common, they use it in trucks a lot. That's 4 microseconds for a bit. That's really slow. But the reason it's slow is because it might be a long bus, and they have to, because of the arbitration time, you have to wait for everybody to have the signal to go on all around the bus to everybody before they can engage in that. But when you're transmitting data, you don't need to, because you're the only transmitter. So CAN HG sticks extra bits in the gaps in such a way that existing hardware doesn't see it and isn't upset by it. And it just ignores it. It's like secret writing.
Power line modulation, kind of almost like you're putting tiny bits on top of a big 50 or 60 hertz swing.
Yeah, kind of like that. In fact, the what actually inspired me was movie film, how they put digital audio.
Yeah, the audio's in right next to the sprocket thingy, right? Isn't it,
exactly.
Like on the side?
So old equipment can play digital film with no problem.
Yep.
And new projectors can play old film with no problem. But if you get new projector and new film, then you get this amazing bandwidth.
Get some richer sound, and compressing that down. That's great. And then it's all about the DAC you have when you reconstruct it, which they can afford.
Yeah. So ours is all silicon IP, so in FPGAs and things at the moment.
So it sounds like they're inherent in all this. It sounds like there's some capacity issues as well. Like everybody's waiting around for their turn. There's so many devices on the network, increasing number of drops on a network. What are the current limits? So let's just say I have a Toyota Corolla. What, most generic car I can think of, at least in the US, like it's got 50 or so ECUs on it. How much data can you shove into there? Like it seems like there are some limitations there.
Yeah, so it's bus bandwidth. So you can go relatively high bus bandwidth, because one of the things I pioneered, and in fact the reason that I ended up working with Volvo on their platform, was in my PhD I worked out how to calculate what the worst case latencies are for priority scheduled buses and priority scheduled CPUs. So you can actually calculate everything will get there on time or not. And then if the calculation says, yeah, then your bus is okay. And if the calculation says, no, it's going to overrun, then it's not. And so you can normally drive the bus load up to sort of 70% quite happily before it starts getting tight. However, with all of the signals and all the stuff going around, some of these buses need way more than just 70%. So they normally partition the vehicle buses. So if you look at the RAV4, where we reverse engineered the wiring diagram part of it is part of that work. So if you look at the
Yeah.
blog post on
Yeah,
that,
we'll have a link in the post here. Yep, for sure.
yeah. So the headlights, I call it a control bus. So the headlights and a few other things. I think there's a radar sensor and the wireless key receiver are on that control bus. Then there's a gateway, and then on another powertrain bus are things like the gearbox and the engine management and the ABS and stuff like that. And then there'll be other buses, perhaps from another gateway through. So probably the RAV4 has, I can't remember, I think it's 5 CAN buses, might be 6.
Okay.
So you typically
Okay.
have one at the back, one around the front engine bay, then one in the powertrain side, and then there may be more. And then hanging off some of the ECUs on that are LIN buses as well.
Okay. Okay.
So you basically get your bandwidth by having more CAN buses.
Okay. That's a great summarization there, I think. Yeah, because one thing I think about is like I remember when they were making the switch over to drive-by-wire, where like the steering wheel is not a physical thing anymore. I remember Mercedes was talking about it a while back, and I know it happens more and more, especially with like driverless. And just thinking about like the fidelity you would need on a signal like that versus your motor versus or your engine rather versus your whatever, just like the amount of data just seems like it's increasing as much as the processing of that data is increasing.
Yeah, yeah. I mean, exactly. What's really given a big jump to the amount of data and then put a limit to CAN is these driver assist systems with cameras. So that's
Got it.
why cars are using Ethernet in some places
Oh,
now.
interesting.
So you've got a kind of a
Uh-huh.
hierarchy of so Ethernet's the highest bandwidth, and there's
Mhm.
CAN, and then down to LIN. But of course, bandwidth and latency are very different things. So for
Sure.
tight real-time control systems with CAN, the bandwidth's quite low, but you're only dealing with very small amounts of data. But for things like cameras that are then feeding into the control systems, you're dealing with very high bandwidth and reasonable latency requirements on that.
Right.
And they can't send the camera data compressed because that ruins all the vision systems because it introduces artifacts that mess up the vision
Oh,
processing algorithms. So you have to have raw
wow.
HD cameras, which is like what, 30 megabits, something like that,
Right. Yeah.
for
Wow.
each
It does
camera.
feel like a waste of pixels. It feels like they would almost like parcel up the sections and then somehow like make it understand which is the most important part at any given time. So like, oh look, the back bumper is about to hit something. Like we're just going to focus on that part of this frame instead
Yeah,
of like this whole thing where like the upper right corner is just some part of the street that you don't care about or something.
yeah. But I think I mean I'm not a massive expert in image processing. I've done a little bit of neural network stuff, but yeah, I think it's you just pile lots and lots of this data in, and because it's from frame to frame to frame, it's also about
Mm-hmm.
things like effectively trajectory discovery and path discovery. So
Uh-huh.
you kind of need all that data, and then it all goes into some centralized, amazing chunk of silicon that can process 6 video
Mm.
streams at full rate. And
Right.
yeah,
Right.
it's really big iron stuff.
I was going to ask about that because it seems like so. Like I said, the Freescale folks came and talked to me about CAN, and those were beefy microcontroller type things, still super fast. But like on the video stuff now, custom silicon from like an NVIDIA or like a FPGA type stuff. I mean, that seems like that would have to really start crunching pretty hard.
Yeah, so that's where your real big iron stuff is coming in.
Mm-hmm. Got it.
But that's not really the control network of the car. So that's kind of a very specialized system, I think. So you'd integrate that
Sure.
with
Sure.
LiDAR and radar and stuff, and then do sensor fusion
Yeah.
for all the autonomous driving or driver assist.
Okay. This is actually really good. This is a good kind of segue to my next question too, which was like, okay, so now we have this division system that's like backing up the car. It's somehow has control. It's passing along control signals to some other part of the car, and a cat runs into the frame, and they're like, you got to stop. And so the camera system has some localized detection of human or cat or something that it says is a bad thing to be running over, and then it passes a frame along to the brakes or passes some data through that gateway. Like so, and again, Ken has sent this blog post. Will have a visual if you're following along, but you have to send a thing to the brakes, which is through a gateway. How do you actually pass through that gateway? How do you address to something on a different CAN bus?
Yes, so from the high end stuff, there'll be some CAN bus on the big iron that's processed it out and decided what to send. And then there's a gateway to CAN, and so it creates a CAN frame message that says apply the brakes because there's a cat there, I don't think it actually works quite at the cat level, but in principle, yes. So there'll be like apply the brakes, and that will go over maybe from that gateway to another CAN bus. I mean, potentially you might go multiple hops of frames that are gatewayed across, and then they end up being picked up by the ECU that wants to hear that there's a cat there. And there can be, because of the way it's a broadcast bus, there can be many ways that you can. So in principle, you publish there's a cat there, and then the system decides is designed for the appropriate systems to pick up whether they want to respond to a cat being there. So I guess you could use the parking brake or something like that instead of the main brakes. But it's designed to publish that. So when you publish something through a gateway, it's transmitted out, and then other gateways might pick it up and copy it out to their CAN buses. So things would propagate out. The gateways have it's quite tricky to get it right. So, and I've seen a lot of poorly designed gateways. So one of the things that CAN provides you that, as far as I'm aware, no other field bus provides is atomic broadcast. So this means that when the sender has sent a CAN frame and it's marked in its CAN controller as sent, every single online device on the bus has received it correctly.
How do you know that? So you said that's part of the thing.
Because of the protocol.
Yeah.
And this is something that not many people know about, and I think a lot of systems, they build it without knowing this, and it works really, really well, and they're like, wow, that's nice, great. And then they go and move it to some higher speed bus like Ethernet or something, and then it all starts to fall apart with really weird race conditions. And the reason is CAN is providing this atomicity. So how it works is you transmit a frame, and then there's a field called an acknowledgement field, and at least one device has to pull a 0 down into that. So you transmit a 1, and somebody has to transmit a 0. And that says that you are on the bus, effectively, because someone can hear you. But if the things like the CRC fails, then there's an error on the bus, and any single one sees an error, it asserts what's called an error frame. And that is 6 0 bits on the bus. And what that does is that there's a bit stuffing protocol in CAN that basically doesn't allow 6 bits of the same sign to appear in the normal frame. So if you send 6 0 bits on the bus, every other CAN controller will go, whoa, 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 whoa. That's an error. And so basically they all resynchronize, and they all realize that the message has failed, and they all dump what they do, and they all go back to starting to receive a CAN frame again. And then the sender has also received that error frame, so it's dumped what it needs to do. And then they all resynchronize, and it has another go, and it keeps doing that.
So if you're on a bus that had okay, so I know that you said the window control might have LIN on the other end, but if it has CAN coming out the back end, and the window controller has a problem, and it starts not being able to say its transceiver gets busted, and it somehow is just spewing out 6 zeros at a time, and it's error. Does that shut down the car?
It depends. It can do.
Really? Okay.
Most transceivers have a little stuck-out fault detector inside them, and they'll just switch off if they see. Normally, I think it's 30 in a row or something, and they go, "Oh, well, that's definitely." Then they'll shut themselves down. So it's hard to do that. But this is how you do CAN protocol hacking.
Okay, it ties us right back in. Yeah. Okay.
Yeah. So most of CAN hacks you see are people just stuffing a frame onto the bus and lying about where it came from, and then getting the car to accept that. So that's how the CAN injection stuff works. You throw a frame on the bus, and
so CAN injection is basically I pretend I'm a key fob, and I say, no, really, I got this. I got it. I'm open. I'm unlocked. Really, come on, man. Yeah, come on, let me in.
Yeah. So you just say, everything's fine, unlock.
Yeah.
But just as a side track, that specific theft device, this is what this extra transceiver circuit is for. This sort of fake transceiver. Because what that's designed to do is to bust the CAN protocol, so that if any device tries to assert an error, it can't bring the bus to a logic 0. So the driver circuit forces the bus to only basically reflect what this theft device is sending. So everybody else is silenced, and only the fake traffic goes on the bus. And that's something most reports haven't picked this up, but proper electronics people will.
So it's basically it's not just shouting; it's also muting everybody else on the phone call.
Exactly, and then so one of the hardware techniques for CAN is to say there are some hardware devices. So NXP makes one that knows what the identifiers it's sending should be. And so when its host is sending, it goes, yeah, you're fine. If it sees that same ID, but not coming from its host, it's like, whoa, that's a spoof. And so what it does is it sends an error frame. It injects those 6 bits on the bus to kill it. And therefore no one receives that spoof. But what the theft device does is silence that error mechanism. So you can't stop it. So the controller sees this fake frame go by pretending to be it, and it's like, stop it, and it can't affect the bus because of the way the theft transceiver works.
Well, I have to imagine it. I'm sure stuff is already in flight to improve this just because of the importance of CAN and all that other stuff. But like, I'm surprised there's not like a key challenge type, like a challenge type of thing when it's like a device sends a packet and then it's like, well, come on, tell me who you really are, right? And then you do a challenge and you have cryptographic verification. I'm probably getting someone else who's like listening to me talk right now and they're like, oh, I'm gonna tell Chris he knows nothing about cryptographic stuff on Mastodon next. But
no, that's a good question.
But like some other way to validate that you actually are what you are, right?
Yeah, and so at the electrical level, there's been these anti-hack systems, but this theft device has proved if you've got physical access to the bus, you can just silence it. So that's really unfortunate because that was a great technique to spot and destroy spoofs. So the only way to fix it is cryptographically, and the only way to do that is to have unique keys for each vehicle, and then the message is kind of digitally signed.
Yeah,
in your 8 bytes. There's not a lot of space left,
right?
And you send that through, and then the other side goes, okay, it came from him. What you can't do easily at the kind of general purpose CAN level is do a kind of a challenge response because it's a publish subscribe bus. So the sender doesn't know that much about the receivers. And that it's not just that's a really good way to do real-time systems, control systems. It's also that they may be free from different manufacturers and may not know about each other.
Right.
The key receiver is sending a thing saying, "Hey, this key is all valid and you can unlock the car," but there may be no relationship at all at the human level or the supplier level between that vendor of that box and the vendors of the other boxes. So CAN kind of reflects this supply chain model, if you like.
Right.
So it makes it very hard. So if you're saying, "Oh, the key turned up and the driver pressed the button," that's fine. It doesn't know how many people need to know that information, so it's not in a position to get like 5 responses from 5 different boxes and stuff. It's just not the architecture that it fits. But you can do some things like this. You can broadcast your "everything is okay" message digitally signed with an authentication code, and then you can roll the authentication codes in a particular way based on a timestamp or a global timer or something like that. And then all the receivers can know that you created that recently enough that it was a valid message.
Wouldn't it make sense to also just, the most important, like the access control parts of a car, like not put those on the bus, like hook them direct to an ECU?
That's possible, but you have to add another wire for these things. Maybe
but that
long limb bus
stops the whole car from being stolen.
Yeah, the trouble is it also is another point where things can go wrong.
True. Yeah, then they get access to that wire, and then it's like the most critical wire in the car. It might be worth popping the hood, whatever.
Yeah. So it's usually this add more hardware doesn't go down very well. I had someone say, "Oh, you just need to put an extra gateway in."
Yep.
And it's like, well, okay, let's say we can get the price of that to $20, which is pushing it. But let me have a little gateway box, $20. Toyota made, I think in the last 10 years, 56 million cars. So 56 million times $20 is about $1 billion. So it's probably better to find a better way than that.
They've got so much money though. It is really interesting that like OEM model like you're talking about too, because there's interoperability and like, some of the, like the Teslas of the world try and be super vertically integrated, but that's just not how these massive auto companies can operate because they need to have specifications and have other people make stuff for them. It's just not how the industry is built.
Yes. And in fact, if you look to trucks, which was the next industry that picked up CAN after the car industry, the entire industry works like this. So there is no kind of OEM in the traditional sense. So
Oh, interesting.
they'll build some pieces, but the truck fleet operator will choose their engines and their gearbox and things like that. So the bits that are there from the OEM have to work with whatever engine and transmission and stuff that the fleet operators pick.
Mm-hmm.
Because they're running 50 trucks or whatever, and you've got some workshop guys that know Cummins stuff. So then that's what they want put into the truck. So and buses work like that too. So the coach builders are the ones that put a lot of the electronics in place. And there you're looking for an industry interoperability system. So J1939 from the SAE is the standard for interoperability of trucks. And every year they publish a big book that says what all the CAN frames contain and all the data and stuff.
Wow. And so that book doesn't exist for cars, is that right?
No, that doesn't exist for cars because it's a much more closed system. Yeah.
Yeah. And so then let's map that to the car industry. So the J 1969, is that right?
1939.
1939. That's built by the operators and in conjunction with the people actually building the pieces that get cobbled together. Who is defining the equivalent at a specific? Is it Bosch? Is it Toyota? Like who in a car stack up? Who's actually defining CAN messages? Like I said, I look at a CAN bus, it's a bunch of nonsense numbers to me, but Toyota knows their numbers, right? And they can decode stuff. So who actually defines that?
So that's normally the car maker.
Okay,
and they have a whole bunch of tools to do that. And then they issue to people that are testing and developing and in the supply chain, they issue what are called DBC files. And they are the magic decoder of all the CAN frames. So if you've got a DBC file and a CAN bus sniffer, it'll decode it all for you. And the DBC files say not just this speed signal is 8 bits and it's in this CAN frame ID and it's blah, 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 and sent this often. It'll also say 0 means this value and it's in kilometers an hour in half kilometer hour increments. So it'll say how the binary translates into SI units and things like that.
Right. Yeah, because they're bit packing like crazy, like you mentioned earlier, in order to get more efficiency, to get more data through. Right.
Yep. Exactly.
Huh. Interesting. And and it looks like nonsense to plebs like me. What happens if so as a pleb, could I get my hand on a Toyota DBC?
Then no. They're certainly not published.
Okay. They're not published, but what if I knew some disreputable characters? Say I went to DEF CON and I went to the Car Hacking Village. Not saying they're disreputable. Sorry, I shouldn't say that. I know people, they're great.
Yeah. So there's lots of kind of like third-party attempts at reverse engineering these things, and so some cars have been reverse engineered, and there are sort of DBC files that are kind of complete that you can have a look at. But of course, these things change from model to model, so each platform will redo all of its messaging and stuff. So it's a hell of a job to keep up with it. So and it might not be right. You're guessing, and a lot of this.
Sure. Yeah.
So if you're a third party equipment manufacturer, say you're making a tow bar or a caravan or something, and you want to plug into the CAN bus so that you know which are the signals for the brakes and the indicators and stuff, you need help from the OEM really, because every model of car will be done differently, and every time they have a new model of car, it'll be done differently, and you'd have to otherwise hire a kind of a hack team to kind of try and reverse engineering the signals you're looking for. Yeah, it's a terrible waste of time for everybody for these things. What really they should be doing is having something Volvo looked at a very long time ago called an accessories bus. So you produce a special CAN bus that's designed for third-party accessories, and it's kind of like nice and safe, transmits only data and some very, very constrained use. So you're not on the main vehicle CAN bus. That would be nice.
Yeah, right. I don't want my iPhone adapter to be talking on the to the wheel, right? Like that is insane. I don't as a user, I don't want that. I don't think anyone wants that really. No. So yeah,
although it'd be nice to listen and know what the how much fuel was left, so you could alert someone that this is your last chance to fill up.
Yeah. Play it through the speaker.
I think that's how CarPlay kind of works. Is they have a defined interface into the infotainment system, and then the infotainment system is on CAN and can convert appropriately.
Which is again risky. I'm sure there's some risk there, but they like a recognized risk
Oh
model,
yeah,
I'm sure.
yeah.
Yeah.
Yes.
Who in the supply chain actually has access to the DBCs? Is it like all the like does the dealer, does the mechanic of the dealer have access to this, or is the
No,
okay?
because there's actually several systems going on a CAN bus. So there's the what I call the application messages, and that's the DBC file that says these are all these things. And then there's a diagnostic system. So on predefined CAN IDs with a predefined kind of higher level protocol, you can say, please connect me to this unit here. Now I'd like to look at its NOx sensor, and I'd like to look at the lambda sensor outputs, and
Got it.
and
Okay.
on all these things. So kind of a turbocharged what's called OBD2.
Aha, that's the port that I can plug into. That's what
Yeah.
my
So
coworkers
so
do.
that was designed back. I think that was mandated in the early 80s
Mm-hmm.
by CARB, the California Air Resources Board, who are smog controllers, and
Yep.
that socket was intended so that when one of the Californian Highway Patrol officers pulled you over, he had a little handheld tester he could plug into that, and then tell if you had a smoker or not. And that was
Uh-huh.
the goal.
Smoker is a emission heavy car. Is that right?
Yeah, exactly.
I never
So
heard
yeah,
that term.
right
That's funny.
now it's not a cloud, but then yeah, basically it'll fess up to being a bad car.
Uh-huh.
So the check
Interesting.
engine light with Homer Simpson's with sticky tape over it
Uh-huh.
can't lie
Yep.
to the police handheld
Yeah.
tester. that was the
Yep.
idea.
Yep.
But it was obviously a very useful general diagnostic test interface. So lots and lots of people sort of
Sure.
started sticking extra things in. So all the car makers started to put their own diagnostic capabilities onto that connector, and and it grew and it grew and it grew, and that's why we have lots of stuff now you can do via these testers.
Got it. Okay. And that's interesting too. My 1988 Honda Accord, they had to shove a pipe into the tailpipe to test emissions when I took it in, and it failed
Yeah,
a couple times. And at my later cars, no need, because it just had OBD2,
yeah.
and yeah, I plug in, they know exactly what's going on because it's published on the bus.
Although we're
That's
probably
cool.
going back to the era now of having to have direct testing because all the software is lying to you. Hence
Oh
the
yeah, thanks
Dieselgate
Volkswagen.
scandal. Yeah.
Yeah. What about, okay, so another thing I was reading about after you and I talked a little bit was kind of the stack, right? So like CAN is there's a physical layer, there's like a physical stack, and that's like a differential bus, and the
Yep.
transceivers detect 0 and 1 like you mentioned.
Yep.
But then one of the things that was confusing to me is that like you move up the stack and they still call it CAN. Is that right?
So CAN is basically the bit signaling protocol.
Okay.
So that's ISO 11898 chapter 3, I think. And that's
Okay.
CAN.
Yeah.
And then it can actually run on different physical layers, but there's a defined one in ISO 11898 that's standard. But there in the early days of CAN in particular, there were lots and lots of different types of CAN physical layer, one wire buses and so on.
Oh.
But the industry standardized on one, and that's so if you go to a component supplier and look for a CAN transceiver, that's the standard transceiver you get.
Okay.
And then there are, so that covers all of the identifier, retransmit, error handling, error counters, and payloads and stuff. And then above that, it doesn't say anything at all.
Oh, really? Okay. Then I must have.
Then you're on
I'll
your
have to
own.
see what I was looking at. Yeah.
People have to define high level protocols.
Yeah. Right. Because, like, yeah, I mean, you mentioned like the bit packing and all the how manufacturers actually decide to create these database files, right, or
Yep.
these conversion files, but someone just layering all that stuff all the way up the stack, right?
Yeah. So mostly the application frames, at least, they'll that's kind of how it is. It's hardwired, and that's because they don't want to put massively complicated higher level protocols on top. You get the frame in, and you just use a lookup table for the ID, and you get the masks and pull out the numbers you want. So that's really fast and therefore efficient and therefore cheap. But then these high level protocols come along. So J1939 has defined the layouts for you in the big book. So that's kind of a high level protocol. And then there are more and more things. So the diagnostics is a kind of a point to point, peer to peer connected protocol. You say, I'd like to connect to this ECU, and now I'd like to connect to that ECU, and so on. And then the payloads are defined for that. So that's like another high level protocol. And then you can kind of carry on up, adding stuff. So there are new versions of CAN in the works, and the latest one is CAN XL.
Okay.
And that has payloads big enough to contain IP packets. So your higher level protocols might start to drop into, UDP and TCP and stuff like that.
Huh. And what is the benefit of doing that sort of thing?
Well, CanXL runs at 20 megabits, up to 20 megabits, so it's a lot faster.
Mm-hmm.
And it shouldn't be any more expensive at the physical layer end. And there's enough transistors around for the CAN controllers. So it's a much, much faster protocol. And they've simplified quite a lot of it. And they're also working on encryption built into the protocol layer itself.
Okay.
And in fact, I'm on one of the working groups for defining how that works. So there's, in the future, near future, we'll have CAN controllers that do all the encryption stuff in hardware, and then you just get your plain text stuff popping out the top of the CAN hardware interface from the register map. Should be nice.
Right. So now, in addition to DBCs, you'll need to have like embed TLS to actually decode all the CAN packets that are going through, huh? Man.
Yeah. I do worry about.
There's a business in the tooling for sure.
I do worry about the complexity of being added.
Yeah.
Yeah.
I guess you'll be using Wireshark soon instead of these other tools, huh?
I mean, you can use Wireshark today.
You can. Okay.
Can.
Cool.
Yeah.
Oh, great.
So
Okay.
I put some Wireshark decoder stuff on open source on my open source CAN hack site, GitHub
Great.
repository.
Yeah.
So you can find out how Wireshark works. If you go to my blog site, there's a whole blog posting on Wireshark decoding of CAN frames.
Okay.
Yeah.
I'll link that in too. Yeah. That's
Yeah.
great.
So I mean, that's not the kind of professional tools, i.e., expensive ones that people use. But Wireshark's. I mean, I like Wireshark. It's a very powerful tool.
Oh yeah. No, I mean like I've used it in conjunction with my coworkers around like Thread, which has like gobs and gobs of layers that I just don't understand all the way. It's like it's just layers all the way down, and at the end you actually get to see like plain text. It's like, oh, that's actually what I wanted to see. That part's magical.
So Thread must be unbelievably complicated layering going on, and
there's a lot going on. Yeah. I don't get it.
It's very scary.
Yeah. So you mentioned CAN XL. I've heard CAN FD, and then like CAN original. What do they call it? CAN classic.
They call it classic CAN or CAN 2.0 because what we call CAN is actually CAN 2.0 because the very first version that Bosch produced had a whole bunch of issues that kind of transpired. So they moved on to version 2 before anything really got widespread. So I don't think you can get any CAN 1.0.
Is there a Crystal Can or Can Zero, or I'm just trying to map it to different soda flavors here, soda types.
Yeah, so it's CAN 2.0 or classic CAN, as people like to call it, CAN FD, CAN XL, and then there's the CAN HG augmentation. Because one of the problems is when they so with CAN FD, that was the first attempt to bump the payload size up and the speed up. But unfortunately, it's not completely compatible backwardly with CAN 2.0 hardware. So if you put a CAN FD frame on a CAN bus that's got a CAN 2.0 hardware on it, it sees there's an extension bit. But the original ISO spec defined that to have a particular value, and CAN FD sets it to a 1. And if it's set to a 1, old CAN hardware throws an error and treats that as an error. So
yeah. So what do they just like then put older stuff onto its own CAN classic bus and then put it through a gateway?
Yeah. Unfortunately, that breaks the atomicity because the gateway may throw the frame away and half the bus is missing it and the other side didn't know. So you've lost that atomic broadcast, which is annoying. And now you've got increased latency through the gateway. And if the gateway doesn't implement priority queuing of the frames properly, you've got priority inversion, which can randomly add huge latency. So it's not a great solution either.
When you mentioned the atomicity as well, so that's the thing where you said each device on the bus has not thrown an error, so you know that it has been delivered successfully.
Yes.
Does that also applies through every gateway? So like every packet. So if I have bus A and bus B, and bus A is really really busy going on, not noisy, busy, a lot of stuff going on. Every single packet also gets through the gateway, or does not also get through the gateway?
No, it's so the atomicity guarantee only tells you that it got to the gateway.
Okay, got it.
And then the gateway will copy that to another CAN controller, and then the atomicity applies to the gateway onto that other segment of the other CAN bus.
Oh, but it does send all the traffic through.
Well, the gateway can if the gateway is operating properly, then it should probably do that. But I've seen them where they've been so badly implemented, they ran out of buffer space because they didn't know how much buffer space they needed because they didn't do the timing analysis. and then it just throws frames away, and then who knows what the hell's going on.
Yeah, when you explain it, I guess I just imagine that there would be some kind of filtering capability in that gateway as well. So you have,
Yes.
yeah, you might have really, so like the ECU, sorry, the ECU, the engine, the actual engine, probably all of its messages about intricacies that are happening between there and the wheel and other things that might be on that bus. I wouldn't think that would matter to the infotainment system, but you're saying it does get published through a gateway up there?
No, normally the gateway would filter as well. Yeah, exactly.
It would filter. Okay.
Yeah,
Okay.
and some gateways will even rewrite, so they will take the sub
Okay.
signals that they need and create
Yeah.
a new frame with just those signals in.
Yeah. Yeah. It does kind of feel like it's like a router, kind of like the router topology in IP without the addressing.
Yeah, mostly they seem to be kind of like a switch, I guess. But
Uh-huh.
yeah, it is that principle. But if you see when it's like IT gear with switches and stuff, and they just throw them away
Mhm.
because they didn't have buffer space, it's no problem. TCP/IP will pick it up and send it again.
Mm.
But you can't do that with real time
Right.
systems.
Right. Right.
Because it's not time to have timeouts and acknowledges
Right.
and
Right.
resends and all of this. So if the gateway, if you have a gateway between two buses, you really, really must implement it properly.
Mhm.
So it needs to effectively have a guarantee that it will never throw away a CAN frame due to any kind of transient overload. So you have to kind
Mhm.
of prove that there isn't going to be a transient overload that throws a frame away. And then when you send it, you must make sure you send it out in the right order compared to frames coming through. But also, you have to send out urgent frames, have to go ahead of least urgent frames on the outgoing side
Mhm.
as well.
Yeah.
So it's quite tricky to get it built right, and lots of people don't. So you then you're then chasing these ghost intermittent bugs. So CAN was just, you
Yeah.
connect it up, everything gets there. It really works nicely. And you go, okay, well, we just need two CAN buses now. And you break it in half, put a box in between, and now weird things start happening. And
Yep.
trying to trace those
The gremlin
horrible
box.
intermittent faults. Yeah.
Yeah. Wow. Interesting.
Yeah. So I think a lot of these faults are caused by poor gateway implementations.
Mm. What's the relative scale of a gateway controller? Is it like a it's not a linear, it's got to be real time like you mentioned. So like is it like a crossover MCU from like NXP or something like that, or
Yeah. Yeah.
what's
So it's
the
normally
beefiness?
yeah, uh, 2, 3, 4, 5, 6 CAN controller on board, S32K, something like that, maybe. Yeah. An
Mm-hmm.
ARM core, maybe a dual core ARM, something like that.
Like
Cortex
a
M.
M7, or like it's not the 8, it's not, nothing's, is anything Linux controlled? I mean, what is it all embedded? What is the
Yeah, all bare metal normally.
Oh, really?
Maybe a
Okay. Wow.
low level real time operating system. The car industry's got a
Uh-huh.
real time operating system definition that's pretty
Uh-huh.
good actually. So yeah, but it'd be very low level.
But bespoke for autos, is that right?
Sorry.
Like a bespoke RTOS, like not like a
Yeah,
commercial RTOS.
yeah. So there's an AUTOS. It's actually I need to write a blog post on it because it's actually extremely clever and very efficient, and it should have been used all over the place where we have embedded operating systems.
Hmm.
Because of the way it minimizes the RAM usage, so it's all fits on on-chip memory. But there's a standard called OSEC that was late 90s, and then there's a subsumed into a standard called AUTOSAR.
Oh, I've heard of that one.
Defines an operating system, and it's really smart because it has these special types of tasks that, and this isn't GAN related, but you trigger a task and it runs to completion and then finishes, and those types of tasks you can get all to run on one single stack. And the total depth of the stack depends not on the number of tasks, but on the number of priority levels that are needed. And you might only need 3 or 4 or 5 priority levels for the different urgencies. And this can turn stack overhead RAM usage from like 100K to 2. I mean,
Wow.
it's a radically efficient way of doing real time operating systems on microcontrollers, and it should really be the state of the art. And when you go around and you look at other microcontroller operating systems, and it's like, first you have all your stack space allocated. Oh, I've got no RAM left. It's a very common experience.
That is true. The sizes of I do a lot of Zephyr, and it is not small. I mean, it's not, and it's just like there's a lot of bells and whistles in there too. You can optimize it like crazy, but that's up. Exercise is left to the user.
Yeah,
It's not the out of the box like I'm sure many of the auto things would have to be.
yeah. It's disappointing because nearly all of your real-time processing can be done with these basic tasks. They're called basic tasks. They're run to completion tasks. So you just kick them off every 10 milliseconds and they just
but
do their thing.
that's not the only thing an RTOS is meant for. It's also for ease of use and speed to market. And,
Yep.
automotive companies have lots and lots of engineers, whereas other companies don't necessarily.
Yeah, but it's standardized. There's lots of vendors for the operating system, and there are lots of tools and performance tests and all sorts. So it's a fully functional real-time operating system that really isn't anything specific to automotive. It should be useful for any kind of bare metal type problem. I mean, if you want to get up into really high-level stuff of like flash drives and things like that, that's bumping into the real-time Linux type end of things.
Right. It is this it's this middling ground that's interesting there. Because, and it's also like, it's even task specific, I'm sure, right? Because like some things need to just completely focus on that like super, super tight timing versus something that might be a little bit looser, but still could benefit from some of the capabilities you're talking about.
Yeah. So you've got kind of like user interface stuff with button presses and things.
Yeah.
And also motor control.
Yeah.
Then mixed into the same device. Then you want to mix all of that real time criticality up.
Whenever I start talking to people about automotive stuff, the implications, the requirements, and then really the implications of design decisions really starts to like smack me in the face of just like, wow, this could have such far reaching. Does that ever get to you? You've been here a long time. You've been doing a lot of important things in the space. Does it concern you? Does it worry you? Like, does it weigh on you? I suppose. I mean, it sounds like you're doing a great job, honestly.
No, sometimes when you look through some code, it can be really quite. Somebody somewhere has said do this, and then everyone has gone and done that, and they're because of abstraction.
Yeah.
And embedded systems abstraction is a bit of a problem because you don't see under the hood of what's really happening. So for lots of computing, abstraction is a way of managing complexity. But for embedded systems, you need to know things because they bubble up from the bottom and really hit you.
Right.
So somebody has said, "Oh, do this," and I've looked at some of the code generated, and it's amazingly huge overheads. You're talking kind of 4 or 5 times the size of the application, and you're thinking, wow. This is the amount of money that you have to spend to get a bigger microcontroller to fit all of that in, multiplied by millions and millions and millions
fleet of cars,
units.
Right.
And you're looking and thinking, did they really know this was like a $20 million decision they made when they said do that?
Right. That's crazy. Yeah.
I mean, I don't know how you do it because the problem with the car industry is you've got purchasing departments and stuff like that, and then engineering decisions being made. And it's very, very hard to make sure the engineering decisions have a kind of a dollar cost attached to them. Yeah, you don't want to do that because it's going to cause this. Right.
I think some of them benefit from their size generally, that they, whereas me as again a pleb buying on DigiKey, a little bit different than, Toyota buying X millions of parts. They get to drive the chip company a little bit more than I might. Best I've got is a podcast that I can complain on sometimes.
No, I've seen chip vendors complain to me. They're saying we're losing money on this part. And the car maker says, "Well, you'll make it up in volumes."
Yeah, that's right. Yeah, exactly.
Yeah. I always go by the DigiKey stuff. I always quite like though because the relative pricing between devices is probably the same as will come out of purchasing. Just the number is different. Right.
Yeah, it takes them 2 years of production to see the same differences, and because you have to multiply by the entire number of cars they make, but it's still percentage-wise the same. You're saying,
roughly speaking, yeah. So if you're doing kind of design work, you have to kind of in the back of your mind guess at what these kind of implications are for cost of like saying, well, now we need a twin core 32-bit microcontroller.
Yeah, right.
And sometimes the answer is just think about your software a bit harder. Don't spend that money.
Yeah. Because like you said, it does have a rippling effect there. On the flip side of that, somewhat negative starter question, how do you feel when you get in a car? I mean, you must kind of smile and be like, I helped. I helped.
I try and keep the two things separate because
I
guess chefs have this problem if they go out to restaurants and stuff.
Actually be able to enjoy the meal without thinking about how it was made.
So when you look
chefs solve that with copious amounts of wine, I believe. I wouldn't suggest that for driving a car.
No, that doesn't make sense.
Yeah.
Yeah, no, I mean, I think as a driver, though, you can get a reasonably good feel for some of the quality of some of the decisions made, because there's some poor decisions do turn up as like glitches in the user interface, or things didn't work the first time you press the button, they work the second time. And that shouldn't be the case for a properly engineered mechatronic system. So, but as a driver, I think you do get a feel for some of these things, particularly infotainment, which is universally terrible.
Yeah, it's not great.
Degrees of terrible.
It's one of my least favorite words of the 2000s, which is a long time now.
IVI, I think, but I'm not giving up on
that. I think if there are any other car people listening, car designers, whatever, I hope their minds are eased by the fact that, again, plebs like me, I am pleased by the smallest things in cars, like, I don't know, being able to unlock the door by pushing a button and it like detects my key and bounces the signal back. Like that's just pleasing for me. Like I'm very easy to please. So,
yeah,
as long as the car goes and it does, has some usability stuff, I'm happy.
Yeah, no, I like it when there's nice little polite features, like when you put it in reverse, the mirrors tilt to help you out and things, or the lights will stay on after you've left the car for just a little bit.
Yeah, that's a good one too. Yep.
I like that.
Versus my 88 Accord that the headlights flipped up and drained the car battery within 20 minutes if I left them on.
I had a 100 Prelude that did that.
Nice.
But the pop-up headlights are nice.
Last question. What's your take on self-driving cars? This is obviously a big area, but Dave, my co-host, says not in 20 years. I'm a little bit shorter, but my personal estimates have been pushed out a little bit. I've been more pessimistic generally. What's your take?
I think Dave's probably right. I think there's a fundamental information knowledge issue. On highway driving, much more optimistic, because it's a very controlled environment, and even with crazy people, you could probably codify all of that. But in terms of street driving, if there's some, the Autonicast podcast has got some fantastic episodes, and the one with Dr. Phil Koopman is my favorite. And he puts up on some of his slides a picture of a kid dressed as a dinosaur on Halloween, and it's like, did you train your vision system to recognize that's a child?
Right. Yeah.
No. And then he said for some of the vision systems, high vis workers on wearing high vis on road repair are invisible, because the systems weren't trained on people wearing high vis, and therefore these people on the road repairing things are not people, and therefore you don't have to
don't worry about the traffic cone, which is shaped oddly like a human.
So I think the complexity of the real world is just you're chasing an ever diminishing long tail of corner cases.
Right. Even the 99.999 acceptance rate means that you're still mowing down 3 kids dressed like dinosaurs or something like that.
So I just don't think you could ever hit that. But as I say, on the highway, I think you could probably get much, much closer.
Okay. Well, Ken, thank you for reaching out first off. I think this has been a really great look at CAN bus, and I couldn't think of a better guest, with your level of experience to come and explain it to us. Sorry if you had to come explain it to us. I should have done more research before I talked about it. But, sometimes we get lucky, and smart people like yourself volunteer. So I appreciate that.
Yeah. Thanks for having me on it. It's been a breeze.
Where can people find your stuff online?
So if you go to my blog site, it's kentindell.github.io. There is lots of posts there. Canislabs.com has a lot of the technology white papers and stuff, and there are links to videos and things explaining some of the concepts of encryption on CAN and things like that. And if you search, I'm on LinkedIn. Oh, and I'm Ken Tindell at mastodon.social.
Awesome. All right. Thanks so much, Ken. We'll talk soon.
Yeah, great.